Hello, hello. Today, doing another waves because I have a test again. I don't know why there's so many physics tests, but there is. I think it's like 3 or something. I don't think I numbered the other ones. You know what? Doesn't matter. Um, first question. First question says calculate whether the sound was significantly different. What? Okay, that is not the first question. Let me find it. Okay, first question says, okay, a musician is playing a flute, which functions as a pipe open at both ends. At a room temperature of 25 degrees Celsius, the flute is played in its fundamental mode and produce a beat frequency of 4 Hz when sounded alongside a 342 Hz electronic tuning oscillator. When the room temperature drops to 10 degrees Celsius, the flute is played again, and the beat frequency against the same oscillator is measured at 5 Hz. Assume the physical length of the flute does not change with the temperature, and that the speed of sound in the air calculated using V equals 331 plus 0.6 t. Determine whether the flute's fundamental frequency was higher or lower than the oscillator at 25 degrees Celsius. Show logical and mathematical steps required to prove this. Okay. So basically we want to know if it's higher or lower than the oscillator at 25 degrees. So what we can do is we want to find the speed of 25 degrees first, which is 331 plus 0.6 times 25, which is 331 plus 0.6 times 5, 346 meters per second, and we don't know the wavelength, so we can't really do anything with the speed, but that will be useful later, I think. But we do know that 342 take f1, let's just say that's for the original frequency, equals 4 Hz, as the beat is 4 Hz. That means f1 could either be 338 or it could be 346 Hertz. And now we need to test which one it is, actually using the second one, which says when the room temperature drops to 10 degrees Celsius, the fluid is played again, the beat frequency against the same oscillator is measured at 5 Hertz. So basically we want to find the velocity again. Velocity equals 331 plus 0.6 times it drops to 10, so 15 25 take 10, which is 15, so it's 331 plus 0.6 times 15, 340 meters per second. And because, well, how do we get each of these frequencies? So this basically means that V equals F lambda, F1 lambda, and V equals F2 lambda. Let's name this 2, let's name this one V1, 1, 2, so that means it is 346 equals F1 lambda, and 340 equals F2 lambda, and it says the physical length of the fluid does not change with temperature and the speed of sound in the question. So that means lambda is the same. So that just means that if we move F1 to the other side, it becomes 346 over F1 equals 340 over F2, as the lambdas are the same. So that just means if we rearrange this, 346 over 340 equals F1 over F2, and let's sub in F1 and let F1 equals, there's definitely an easier way to do this, but this is way easier to think about. than the other ways, and essentially you can't get this wrong. So 346 over 340 equals 338 over F2. That just means F2 equals 346 divided by 340 divided by 338. And then 1 divide that. So we get 332.14 hertz. Let's test that to the thing. So that just means because the second part says the fluid is played again, the beat frequency against the same oscillator is measured at 5 hertz. So 342 minus 332 is equal to 3, 4. Okay, I know it's 10. It's 9. Okay. 0.14 equals 9.86 or beats or hertz, which is not 5 hertz. So that means F1 cannot be 338, and F1 equals the other one, 346 hertz. Let's test that. So 6 over 340 equals 346 over F2. That means F2 equals 346 divided by 340 divided by 346. And we want to divide the answer. We get 340 hertz, an exact number. I feel like it's probably the answer. So we use 342 to, okay, never mind, it's not the answer. It is not the right answer. What am I doing? Wait, 342. Am I doing this right? Am I doing this right? Yeah, it dropped 10 degrees. Okay, I can't read. It did not say drop 10 degrees, it's dropped 10 degrees. So wrong here. So it is 10. And 331 plus 0.6 times 10 equals 337. Okay, that's pretty dumb. So that becomes 337. 337. 337. Let's test F1 equals 338 again. 346 divided by 337 divided by 338. 1 divided by answer. 329.21. See that? It still should be wrong, I think, because that's a very weird answer. And 342 minus that equals 12.79 hertz. And it's not 5 hertz, and it's not, that means it's not that. 337 as the 346 is cancelled out. 337 equals, it indeed equals 5, yay, and 5 equals 5 hertz. That means F1 equals 346 hertz, and they want us to find higher or lower than the oscillator. Fluid's fundamental frequency is higher or lower than the oscillator. Okay, so the oscillator is 342, and it's bigger than 342 hertz, so it's higher than oscillator. Okay. Now we can move on to the second part of this question. I don't know why it took so long. I mean, I do. It's just a bad way of doing it. I think if you just do the proportional things, it'll be way easier. But this way, I actually use numbers to calculate it, so it can't be wrong. So yeah, exact length of the flute. So that's just V equals F lambda. So F1 equals F1 lambda. So V1 equals to 346. 46 equals to 346 lambda. So that means lambda must be 1 meter. Oh wait, no, because lambda is 1 meter, you're right, but it wants to find the length, And we know the equation that because it's open pipe 2 length over n equals 1, L equals 1 over 2 equals 0.5 meters. That's it for this question. Second question says a speaker emits a continuous tone of 385 Hz in a room with air temperature of 30 degrees. Ooh. The sound travels directly towards the open doorway with 0.9 meters. Immediately past the doorway is a long sealed hallway where the temperature is heavily cooled to 10 degrees Celsius. Assume the significant diffraction occurs only if the sound waves is greater or equal to the width of the gap. Calculate whether the sound will significantly diffract as it passes through the doorway from the warm room. So you want to find the wavelength of the warm room. So as we use the equation from the last question, we want to find the velocity of the sound from the warm room, which equals 331 plus 0.6 times 30, 349 meters per second. And travels doorway is 9 millimeters. Now we want to find the actual wavelength. So V equals F lambda, which means 349 equals 385 lambda, and lambda equals 349 divided by 385, which equals 0.906 meters, and 0.906 is bigger than 0.9 meters of the doorway, which means as wavelength greater than door way width, it will diffract kind of slightly, I would say, because it's only a little bit bigger. Part B, explain using physical principles and relevant equations, explain what wave velocity, frequency, and wavelength. What happens to the wave velocity, frequency, and wavelength as it crosses the boundary into the cooler hallway? So basically, when I explain each by each, frequency is easy to explain, so it's the same. Well, frequency must be constant as it is determined by the oscillations that created as temperature is proportional to velocity to sound velocity will decrease in the cool room, leading the wavelength to also decrease as V equals F lambda, with F being constant. Okay, that's basically how you explain. Can you explain better, I guess? Third part says, will the sound wave become more directional or more spread out after entering the hallway? So it's after entering the hallway. So as the temperature cooled in the hallway, so it's still heavily cooled to 10 degrees Celsius. The new wavelength need to be
calculated. So F equals V lambda. That means is 331 plus 0.6 times 10 degrees equals 385 lambda. That means lambda equals 331 plus 0.6 times 10 equals, and divided by 385. 0.875 meters, 0.875 meters, smaller than 0.9 meters, smaller wavelength, smaller than doorway, width, therefore the sound wave will diffract less, making it more directional, going into the cooler room. I think that's a decent explanation. So, oh well. Bye bye.